So I'll be explaining the branch and bound feature selection algorithm. So before moving on to the algorithm, I will give a brief background. In machine learning, the curse of dimensionality refers to the problems that arise when working with high-dimensional data. The dimensionality in a dataset refers to the number of attributes or the features that the dataset has. So if there are a large number of attributes or features, then it is referred to as a high-dimensional data. But the difficulties arise related to machine learning training machine learning models due to high dimensional data, and these difficulties are referred to as the curse of dimensionality. So this graph shows the curse of dimensionality curve. The x-axis shows the dimensionality of the number of features, whereas the y-axis shows the classified performance. So initially the performance is increased, but then if you keep on increasing the number of features, the performance decrease. So up to a certain number of features, the accuracy of a classifier can be increased, but then there's a threshold after which the performance starts to decrease. Because of this, the optimal set of features has to be found to mitigate the curse of dimensionality. This challenge has motivated to find many different feature selection algorithms over the past decades. Branch and bound is one such algorithm developed by Narendra and Fakunaga in 1977 for feature selection. So basically, the branch and bound algorithm is used for minimization problems. So this is a brief introduction about the algorithm. It basically follows a tree structure to select the best set of features, and it assumes that the feature selection criterion is monotonic. It can find the best set of features without having to evaluate all possible subsets. Therefore, it doesn't involve exhaustive search. So there are two main steps in the branch and bound algorithms as branching and bounding. So branching basically involves constructing the tree. So when you're constructing the tree, for each tree level, a limited number of subtrees has to be generated by deleting one feature from the set of features in the parent node. And the bounding is basically the process of finding the optimal feature set by traversing the constructed tree. So let's look at an example. Suppose you have a dataset which has 6 features as F1, F2, and likewise up to F6. So you need to find the best 2 features from these 6 features. So we have to start by identifying the properties of the tree. The first property is the number of levels. So since we have to select 2 features from the 6 features, 6 minus 2, the number of levels that in the tree that we are going to construct is 4. And then the number of leaf nodes, so that is 6 combination 2, which is equal to 15. So let's assume that the criterion function value is jx. So we have to then start constructing the tree by branching. The root node has to have all the features. So this is my root node. I have added all the features F1, F2, F3, F4, F5 and F6. Then the intermediate child nodes has to be created by reducing one feature from the parent node. So here I'm removing F1 feature and creating this node. And then I'm going to remove F2 and I create this, and then I remove F3 and create this node. So as you can see here, I removed these features in the ascending order, and that was done to avoid the chances of subsets getting duplicated. So this is my level 1. Also, you may have noticed that I did not remove F4, F5 and F6 features to create 3 other child nodes. So I did not remove F4, F5 and F6 features initially, because if I do so in the beginning, I will not have features to remove in the next level. So you have to follow the process until leaf nodes are reached. So this is the level 1 I showed in the previous slide. And then again from those child nodes, I have to remove one feature and create these child nodes. So this level 2 is created, and then so for example here, this is the child node I created earlier with the features F2, F3, F4, F5 and F6. So I removed F2 and created this node, and I removed F3 and created this node. I removed F4 and created this node. So likewise, I have removed one feature and created this. So that is level 2. So level 2 has nodes with 4 features. Then again, I have to remove one feature and create the other child nodes. So here, from this node, I have removed F3 and created this node. And again, I have removed F4 and I have created this node. And I have removed F5 and created this node. So likewise, I have to follow the process. So as I explained earlier, I have removed the features in the ascending order. So that is level 3, and in the level 4, I'm left with subsets of 2 features. So in the last level, I'm left with 15 15 leaf nodes, which has 2 features. Then we need to calculate the criterion function Jx for the subsets that we created. So just to show you, I have assumed some values for this criterion function here. So for example, in the period node criterion function value, I have set it as 220, and the immediate child node criterion function values are set as 13, 18 and 15 likewise. So then I have to start bounding and pruning. Pruning is basically the process of removing the unnecessary leaf nodes. Then we have to start with the rightmost node. We have to set the rightmost leaf node value as bound. So the rightmost leaf node value is 9. Therefore, our current bound value is 9. Then I have to backtrack along the tree if the current node value is greater than or equal to the bound value. So if I go back, so now here the bound value is 9, and then if I go back to here and go to this node 18, which is greater than 9, so I continue and come to this 16. So again 16 is greater than 9, so I'm going to continue, and 10 is greater than 9, so I'm going to continue, and I come to this leaf node which has a value 7. And I need to update the bound value only if the leaf node value is greater than the bound value. So here the 7 is not greater than the bound value, which is 9, so I'm not going to update the bound value by 7. So my bound value remains as 7, and then again I'm going to backtrack, and I'm going to come through this node and continue, and I come to this leaf node which has a value as 10. So 10 is greater than 9, therefore I need to update my bound value as 10. So the current value is 10 and my bound value is also 10. And I can discard or prune branches if the current node value is less than the bound value. So for example, now the bound value is 10. So then if I again go through this, and this has a value of 9, so which is less than 10. Therefore, I do not need to continue through this node, so I can remove it. And then if I again go back and come to this, so this has again a value of 8, so which is less than the bound value 10. So I do not have to continue that branch. So since I'm not left with any other branches to proceed, my the maximum bound value is equal to 10. So 10, the subset with the criterion value 10 is this. So that has the features F1 and F4. Therefore, the optimal feature subset is F1 and F4. So this is a pseudocode of the branch and bound algorithm. So it shows how we can select a new node and go to this node, and we need to check the bound, and then we need to backtrack to a lower level, and likewise we have to proceed. So then I will demonstrate how this algorithm works in RStudio. I'm going to take a dataset from the UCI repository. So I have gone to the UCI repository website, and I will select a dataset to demonstrate how the branch and bound algorithm works. So I'm going to select this absenteeism at work dataset. So it has, so you can see a basic details about the dataset here. It has a number of instances, so 740 instances, and 21 attributes. So I will download the dataset. Sure, this Word document has some basic information about the dataset. So let's first look at it. So it has, as we saw earlier, it has altogether 21 attributes. So this has some information about those 21 attributes. For example, the first attribute is about the individual identification, and the second one is the reason for absence, that is ICD coded, and then the third attribute is the month of absence, and the fourth attribute is the day of the week. So the fifth one is season. Likewise, we have 21 attributes, and this the last one is the absenteeism in a time in hours. So let's go to RStudio. Um, so I am going to show how this algorithm works using the Leaps library. So I will first import the library. So this absenteeism at work is going to be my data set. I will comment it, and then I have to yeah, we will have to then import the data set. I'm going to import the data set to RStudio. So this is the data set, and yeah, I'm going to import it. So this is the imported data set with 21 attributes, and I can view the data set from here also. So here's the data set, and then I am going to define the x and y variables. So x variable, will first define the x variable. So x variable, I'm going to say model dot matrix, and I have to select my response variable. So the response variable has to be this absenteeism in time in hours. So I will have to set it as the response variable. Absenteeism time in hours. So let's see if that's the correct name of the attribute, absenteeism time in hours. Yeah, so I have set the defined, yeah, I have set the response variable, and then this is -1 is um, to take the intercept out, and this I am going to set the dataset I imported as the dataset that has to be used here. Then we'll run it. Okay, and now I have defined x and I need to define y. So this is the dataset, and then the response variable, and then I will run it. Now I have defined the variables x and y. Then we need to fit the x and y variables using the leaps function. So I have set best modes is set to leaps x, y, and in best I'm going to select the best one best model. So we'll run it, and let's see what now we have run the model, and let's see what the models are. So here are the models, and I get so these the columns represent the attributes. So the false means the ones with true are the the features that it suggests. So for example, if you want the best model with only one feature, then this is one such model which only has the second attribute. That is, let's see what the second attribute is. The reason for absence, so it only has that and it does not have the other attributes. And the second model that it suggests has two attributes, that is this, the reason for absence, and then this one. So that has to be uh, yeah. So since it does not have enough space, the so we have altogether 21 attributes, and I removed the response variable, the last one. Here I removed it by um, I have removed it. So because of that, so I have 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21. 21 attributes are shown here. So in the second one that it suggests has only two features, that is the second one, and then the 12th one. The 12th attribute, let's see what the 12th attribute is from here, that is the disciplinary failure. And the third module has three features, the second one and the this one, that is the one we looked earlier, the 12th one, disciplinary failure, and also the 14th, the 13th one, that is the education. So likewise, it suggests several models with the number of features that we want. So for example, if we want say 5 features, then we have to go for this one. So the ones which has the value as true are the features that we have to select. And likewise, it has suggested 20 models, and these are the label value, the label name set for the attributes. And yeah. So then we are going to use the malloc cp function to find the best model. So we will run this. Yeah. And to find the best model, we have to select the model with the least malloc cp value. So we will run this. So this is the least value, 5.952. So let's see which model has that value. So this is the one. 9, 10, 11. That is the 11th one. So the 11th one, let's see what it is. This. So the best model would be the model with these 11 features. That is the first one, which is the first feature, which is the individual identification, and then the second feature, which is the reason for absence ICD coded, and third one we do not have to use, and then the fourth one, which is the day of the week, and fifth one we should not be using, sixth we should not be, and seventh we have to. So the seventh one is the distance from residence to work in kilometers, and that was the seventh one. And the eighth one we don't have to use. The ninth one we have to use. Ninth one is the age. Likewise, this is the best subset that it suggests. The best subset has 11 attributes out of the 21 attributes.